afternoon we're going to be working problems from Chapter 2. Now there is one from Chapter 1 we'll start out with. So we're on page 116 of your lecture notes and practicing some problems, especially from Chapter 2 today. A lot of these are old test questions, and this will help you as you focus on learning the material in the chapters. Okay, so number 15, this is a dimensional analysis problem. It says the volume of a certain bacterial cell is 2.25 cubic micrometers. What is its volume expressed in cubic millimeters? Okay, well, in order to solve a problem like this, we're going to use dimensional analysis, which focuses on the units. There's 3 steps we always follow. Number 1, write down what you want to know. And by that I mean I'm going to put the number sign and the unit that you're looking for. I'm looking for the number of cubic millimeters cubed. And I put that on the left side of the equal sign. So number 1, write down what you want to know. I want to know the number of cubic millimeters. This is helpful because as I proceed through the problem, it will tell me if I'm making progress in the right direction. Number 1, write down what you want to know. Number 2, start with the given measure quantity, which is this number. Now, when you write that down, write the full unit down. So 2.25 cubic micrometers. Cubic micrometers. Now, this is an old test question, so this will give you an idea of the kinds of questions that can be asked. Number 3, apply conversion factors in order to cancel unwanted units. Okay, well, here's what you need to know. You need to memorize the table of metric prefixes. And from the table of metric prefixes, milli means 10 to the minus 3, and micro, which it looks like a U, but it's got a tail on the front end of it, micro means 10 to the minus 6. And so I don't want it in micrometers, I want it in millimeters. And so what we should do here is say times, draw a line, and put micrometers in the denominator. And the first thing that you do is you go from micrometers to meters. You don't want to take a shortcut here. In class, I talked about the fact that that's a bad shortcut if you try to take a shortcut here. And we go from micrometers to meters. Now, micro means times 10 to the negative 6. And so, since that's what the metric prefix means, it means 10 to the negative 6, you put the 10 to the negative 6 with the unit that does not have a prefix, with the base unit. So, 10 to the minus 6 meters is equal to 1 micrometer. So a real common mistake is to put 10 to the minus 6 with the wrong one. But micro means 10 to the minus 6. So that's like saying 1 micrometer equals 10 to the minus 6 meters, because micro means 10 to the negative 6. So you memorize those metric prefixes. The exponential term is 10 to the minus 6, and it always goes with the base unit, the unprefixed unit, the meters without the prefix. Now, if 1 micrometer is equal to 10 to the minus 6 meters, is it also true that 1 cubic micrometer, 1 micrometer cubed, is equal to 10 to the minus 6 meters cubed? Is that true? No, it's not. In fact, we would say in class, heck no. Heck no, you can't just cube the unit, you have to cube the entire quantity. So 1 cubic micrometer is equal to 10 to the minus 6 times 10 to the minus 6 times 10 to the minus 6 cubic meters. If I can't just cube the unit, I have to cube the whole quantity. So I'm going to put this whole thing in parentheses, and this is cubed. So now, the cubic micrometers cancels, and I have it in cubic meters. But I don't want it in cubic meters, I want it in cubic millimeters. And so I'm going to say times, draw a line. If I don't know anything else to do, I don't want it in cubic meters. I'm not writing cubic meters down here, I'm just writing meters. Because meters, the base unit, is not cubed. And so I look at this, and milli means 10 to the minus 3. And therefore, 1 millimeter equals 10 to the minus 3 meters, because milli is another way to say 10 to the minus 3, or 10 to the minus 3 is another way to say milli. So I'm going to go from meters to millimeters. And milli means times 10 to the minus 3. You always put the exponential term you memorized with the base unit, the unprefixed unit. So 1 millimeter is equal to 10 to the minus 3 meters. Okay, so if you've heard me ask this enough, you know what I'm going to ask. If 1 millimeter equals 10 to the minus 3 meters, is it also true that 1 cubic millimeter equals 10 to the minus 3 cubic meters? No, or we say heck no. Heck no, you have to cube the whole quantity. You can't just cube the unit if it wasn't cubed to begin with. You have to cube the entire quantity. Now be sure you plug this into your calculator and you know how to use the scientific notation. You know how to use the cube terms correctly to get the correct answer. And this calculates out to be 2.25 times 10 to the negative 9 millimeters cubed. Okay, so that's another Chapter 1 dimensional analysis problem. Okay, do you all have a question or comment on that? Okay, so let's look at the next question. I mentioned in class today that I really could not do an atomic weight calculation off of an element on the periodic table, because all you would have to do is, if I ask you to calculate what's the atomic weight of silicon, you would just look on the periodic table and say, well, it's 28.086, right? So, or is that an 86? Yeah, 86. You would just look on the periodic table. Now I want to know, can you calculate it? So this is one way the question could be asked. One way the question could be asked is to give you an imaginary element. So Im is an imaginary element that has two isotopes. Im30, with this is the mass, the isotopic mass. The isotopic mass is the mass of this isotope, the Im30 isotope. And this is the percent abundance of that isotope. And Im31 with this mass and this percent abundance. Okay? So there's two isotopes. What is the atomic weight? The atomic weight is the same as the average atomic mass. And the way that we do this, before I plug the numbers in, let me just set it up using words. Atomic weight of, in this case, of the element In is going to be equal to the fractional abundance of Im30 times the mass of Im30 plus the fractional abundance of Im31 times the mass. This is called a weighted average. We're taking a weighted average. We convert the percents to fractions and take the weighted average, the mass of Im31. Now, first of all, I want you to be sure that you understand the terminology fraction, because we'll use the word fraction a lot. I know that you know what fractions are, but let's go back to our junior high definition of percent and fraction. The junior high definition of percent is what? What is a percent? The part over the whole times 100%. The part over the whole times 100%. Now, this is a simple definition, and anytime in chemistry we use percent, we almost always use this definition. So that means all you have to do is figure out what the part is and what the whole is, and you can calculate the percent. And then the junior high definition of a fraction is the part over the whole. So look at the relationship between these two. That says if the percent abundance of this isotope is 20.78%, then the fractional abundance is 0.2078. You just move the decimal place 2 places over. The difference is a factor of 100. If 50% of this class is female, then the fraction of this class that's female is 0.50. Okay, so you change the percent to a fraction. That's what a fractional abundance is. Okay, and so the atomic weight of this imaginary element is equal to the fractional abundance of Im30, which I convert the percent to a fraction. I move the decimal place 2 places to the left. So this is going to be 0.2078 times the mass of Im30, which is 30.013. That's for Im30, plus the fractional abundance of Im31. It exists as 79.22%, so we move the decimal places 2 places over, 0.7922 times the mass of Im31, which is 31.008. Now, when we do this, we get this calculator answer. The calculator answer is 30.801 239, And I always like to put the calculator answer in brackets. Remember, your calculator does not know significant figures. So to determine significant figures, we almost have to go back and do the calculation twice, especially when a calculation like this has both multiplication and addition. Now, if all we were doing was multiplying or dividing, we would just count sig figs and go with the least number. But if any time you have either adding or subtracting, you've got to go back and be very careful about this. On ALEKS, a lot of people had a tremendous amount of problem on that first ALEKS assignment, the fundamentals assignment, with the significant figures, because when they added and subtracted, they used the wrong rule. So when you add and subtract, you don't ask how many significant figures, you always ask what? How precise is it? So to get the correct number of significant figures, we're going to go back and do this one step at a time, applying the appropriate rule. So the first thing we'll do is multiply. And when I'm multiplied, my calculator gives me 6.2367. But what question do I ask when I multiply? How many sig figs? So how many sig figs should this have? 4. This has 4 sig figs, this has 5, so the answer must have 4. I'm going to underline the significant figures. Plus, now when I multiply this out, my calculator gives me 24.5645. But again, when I multiply, I ask how many significant figures, and how many significant figures should that number have? It should have 4. This has 4 sig figs, this has 5, so this should have 4. 1, 2, 3, 4. Now when I add, what question do I ask? I don't ask how many sig figs, I ask what? How precise. How precise is this number? The 1,000ths place. And how precise is this number? The 100ths place. Now I've written more digits, but I've underlined the significant ones. So which is less precise, the 1/1000th or the 1/100ths? 1/100ths. And so here's the 1/100ths. And so the answer is 30.80 atomic mass units. That's called the atomic weight. We call it the atomic weight because it is a weighted average. And of course, one thing that I emphasize here, even if this were a real element, there would not be a single atom in the world with this exact mass. It's an average mass. It's a weighted average. There are two isotopes. This is the mass of one, this is the mass of the others. None of them have this exact mass. This is just an average mass. Now, the purpose of the problem sessions is to be real informal. And if there's anything that I did that's not clear, this is a good place to ask, and I'll try to elaborate on it. So is there anything I can help any of you with on this? You see how I did that? Is everybody good? Okay, so there's two ways I could ask an atomic weight question. One is to make up an element, like this one, this imaginary element, give you the mass and the percent abundances of the isotopes, and you get the weighted average. Another way is if you have an element that has only 2 isotopes, you can determine the percent abundance of each one. So this is true of boron. This says boron has 2 naturally occurring isotopes. Boron 10 with this mass and boron 11 with this mass. And then you have the average atomic mass. Now what's another term for average atomic mass? Atomic weight. So the atomic weight, or the average atomic mass of boron, is 10.811. What is the percent abundance of boron 10? What is the percent abundance of boron 10? And so when I set this up, I'm going to set this up in words just like I did this one up here. And it's just to show you, this is just a weighted average, just like when you calculate your grade in the class. So the atomic weight, before I plug in any numbers, the atomic weight of boron, there's 2 isotopes, boron 10 and boron 11. So it's going to be the fractional abundance of boron 10 times the mass of a boron 10 atom plus the fractional abundance of boron 11 times the mass of boron 11. So that's what we have. We'll just plug in the numbers to get it. So we're given the atomic weight of boron. The average atomic mass, or the atomic weight of boron, is 10.811. So 10.811 equals. Now we don't know the fractional abundance of the 2 isotopes. So I'm going to call the fractional abundance of boron 10 X and the fractional abundance of boron 11 Y. I know the mass of boron 10. The mass of boron 10 is 10.0129, and I'll say that's times X, where X is the fractional abundance, 10.0129 is the mass. Plus the mass of boron 11, which is given, 11.00931, times the fractional abundance of boron 11. Let's call that Y. And so this goal is to determine the fractional abundance. Now, in algebra, we learned that one equation with two unknowns cannot be solved. So do I choose choice E, not enough information? No. Even though this has two unknowns, since there are only two isotopes, what do you automatically know? They add up to 1. The 2% would add up to 100%. And so the two fractions add up to 1. You know, if I told you that 65% of the class is female, you automatically know 35% of the class is male. It adds up to 100%. So I'm going to put important X plus Y is equal to 1. And since we're looking for the fractional abundance of boron 10, which was X here, I'm going to let Y equal 1 minus X. And I'm going to plug that in right here. I'm going to let Y equal 1 minus X. So I'm going to have 10.811 equals 10.0129X plus 11.00931, and Y is 1 minus X. So they both add up to 100%. So all we have to do is solve for X. Now, the first thing I'm going to do is I solve for X. I'm going to draw a line and solve the rest of it over here. I'm going to collect all my X terms on the left side. So, well, no, actually, first I need to multiply across to remove the parentheses. I think I'll do that one more line here. 10.811 equals 10.0129X plus, and I'm going to multiply this across both terms, 11.00931 minus 11.00931X. So all I did, I just multiplied across to remove the parentheses. Now I'll get all of my X terms on the left side. So I'm going to get this term on the left side, the equal sign, I'm going to subtract this from both sides. And so on the left side, I'll have negative 10.0129X. And I'm going to add this term. I'm going to add 11.00931 to both sides to get this out of the right-hand side and get to the left-hand side, plus 11.00931X equals, and I'm going to get the number terms on the right side. Now, I already have this number term on the right side, so 11.00931, and I'm going to subtract 10.811 from the right-hand side. Did I do all that right? Okay. So I'm going to get my X terms on the left side of the equal sign and my number terms on the right side. Now, when I subtract these two numbers, my calculator gives me 0.99641 X. And that's equal to 0.99641X. That's equal to, and when I subtract these two, my calculator answer gives me 0.19831 as that number. And then when I divide that out, X is equal to 0.19831 divided by 0.99641. And my calculator answer here is, let's see, my calculator answer, 0.19831 divided by 0.99641. And I get 0.199024498 is my calculator answer. So in order to determine significant figures, let's go back. You know, a lot of the times, in order to get the correct number of significant figures, what you have to do is you have to go back and do a calculation twice. You do it once all the way through without any rounding to get the best calculator answer. By the way, you have to do that in ALEKS. You go all the way through to get the best answer using the calculator. answer. One student told me today that they especially liked in ALEKS using the calculator in ALEKS. If you use the calculator in ALEKS and you need the mass of one of the atoms, it'll pull up the periodic table, you click on that element, and it will insert that number in there, so it'll save you time. Okay, so you have to do this again. Now I've got the calculator answer, I have to go back and look at it step by step to determine the number of significant figures. So here first I'm subtracting. And when I subtract, what question do you ask for significant figures? How precise? How precise should it be when I subtract these two numbers? To the fourth decimal place. This is 1, 2, 3, 4. This is 1, 2, 3, 4, 5. To the fourth decimal place. That's the 1/10,000ths. So to the fourth decimal place. 1, 2, 3, 4. And when I subtract over here, how precise should this side be? To the 1,000th place. 1, 2, 3. Now when I divide, what question do I ask? How many sig figs? How many sig figs should I have? 3. It's 3 because when I subtracted here, I was only precise to the 1/1000th place. This only has 3 sig figs. So the answer will only have 3 sig figs. Now X, remember, that was the fractional abundance of boron-10. The question says, what is the percent abundance of boron-10? So therefore, the percent abundance of boron-10 is equal to, I moved the decimal place 2 places over, 19.9%. The best we can get, the best number of significant figures we can get in this calculation is 3 significant figures. Even though I have a lot more significant figures in every case, this has 6 significant figures, this has 7 significant figures, this has 5, and yet the best we can get is 3 significant figures. Remember, if adding and subtracting is involved, you can't just figure out the number of significant figures by counting the number of sig figs in the numbers. You have to go step by step, especially watching where you add and subtract. Okay, and that's the boron-10. If I'd been asked what is the percent abundance of boron-11, how would I get that? I would subtract this from 100%. Any question on that one? Yes?
So for example, if the number is like 1997, do you round it to like 20?
Yeah, if this were 0.1997, I would round it up, and it would be 20.0%. It'd be 20.0%. If there were a 7 here instead of a 0, it'd be 20.0%. It would still have 3 significant figures there. Okay, another comment or question? Okay, now what we're going to do is we're going to name some ions on the next page. And before we name some ions, let's take this blank periodic table and talk about how we name ions. So in my class, this is a little ahead of where I am in class, so you'll get a preview for what I'm going to talk about in class. Now the purpose of the periodic table is you have to know the charges of the monoatomic atoms from the periodic table. And in group 1, so this is group 1, where we have hydrogen, lithium, sodium, potassium, rubidium, and cesium. The elements in group 1 want to be like the noble gases over here in group 18. So here's the group 18 noble gases. And they can do that by losing 1 electron. If they lose 1 electron, they become positively charged. Remember the joke. I lost an electron. Are you sure? I'm positive. So they have a +1 charge. So these want to acquire a +1 charge. So these will form stable ions with a +1 charge. So there's nothing to memorize there. If it's in column 1, it will form a +1 cation. The atoms in group 2 will lose 2 electrons. If they lose 2 electrons, they'll have the same number of electrons as the noble gas nearest them. So in group 2, we have beryllium, magnesium, calcium, strontium, and barium. Calcium, strontium, and barium. Now, you don't have to remember these. You will always have a periodic table in front of you on the exam. Now, over here, neon is very stable. It's a noble gas. It's extremely stable. It does not react with anything, very many things. So it's actually, I don't know of neon reacting with anything. There may be some unusual case where it will react. A neutral neon atom has 10 electrons. Well, magnesium wants to be like the noble gas nearest it. If it loses 2 electrons, it will have 10 like neon. So the group 2 elements will all lose 2 electrons, and they'll form a +2 cation. We write it 2+, 2+, 2+, 2+, and 2+. So there's nothing to memorize. For the cations, they acquire a +2 charge. Now, we have this stair-step line over here separating the metals from the metals. Metals on this side tend to lose electrons and become positive. Nonmetals tend to gain electrons and become negative. So here's magnesium, +2 in group 13. Here's aluminum, which is a metal. It will form the 3+ cation. And the reason that aluminum forms the +3 cation, if you look at this periodic, the periodic table here, aluminum has 13 electrons, a neutral aluminum atom. By the way, when I say atom, what am I trying to emphasize? When I say the word atom, what am I trying to emphasize? That it's neutral. Aluminum has 13 protons, and an aluminum atom has 13 electrons. But if it loses 3 electrons, it will have 10 electrons, like neon, in front of it. And so aluminum forms the +3 cation. So you have to know that those are the charges of the stable monoatomic cations. Now there are 2 more that you have to memorize, and they're easy to remember if you remember that aluminum is +3. Right here is zinc, and right here is silver in this diagonal. So we have aluminum, zinc, and silver. If you remember that aluminum is 3+, that will help you remember that zinc is always a +2 and silver is always a +1. And so you have to memorize those. Actually, it's not so much memorizing. It's right on the periodic table. Now, any other metal can have more than one charge. It's a variable charge cation, and so we use Roman numerals for any other metal. And for example, if I were to list, right here is iron. And iron is 1, 2, 3, 4, 5. It's the 6th one in this block. 1, 2, 3, 4, 5. Here's iron. And iron can form Fe2+ or Fe3+. So you don't have to memorize that. The way that we name that, the name gives it away. Fe2+ is called iron 2. So we use a Roman numeral 2. And the Roman numeral 2 tells you it's a +2 cation. Fe3+ is called iron 3 with a Roman numeral 3. So all of these down here can form all kinds of charges, and you don't have to memorize the charge. The Roman numeral will give it away. Or if I give you the charge, you know the name. It's named with the Roman numeral element here. So for example, if I look right here, we would have, this is lead, Pb. Now lead has more than one charge. So it has more than one charge. And if we were to say Pb2+ or Pb4+, those are 2 ions that lead forms. Well, you tell me, what is the name of Pb2+? This is lead 2 with the Roman numeral 2. Lead 2. What's the name of Pb4+? It's lead 4 with the Roman numeral 4. So there's nothing to memorize. So which ones you memorize? You memorize that column 1 is always +1, that column 2 is always +2, that aluminum is always +3, zinc is always +2, silver is +1. And then all the others, the name will give it away. If I say iron 4 or iron 3, that means it's Fe3+. Okay. Next, you need to know the names of the anions. The nonmetals tend to form anions. Over here, they tend to gain electrons and form anions. So this is group 14, 15, 16, 17. So if neon is very stable because it has 10 electrons, well, fluorine is right next to neon, and it has 9 electrons if it's a neutral atom. But if you give it one more electron, it's stable like neon. So we have fluorine, chlorine, bromine, and iodine. Each of these want one more electron. Fluorine becomes fluoride, chlorine becomes chloride, bromide, and iodide. They end in IDE. So there's nothing to memorize. If it's in group 17 and it forms an anion, it's always -1. Group 16, here's oxygen, sulfur, selenium, tellurium. Oxygen becomes oxide, which is 2-. It needs 2 more electrons, so that it has the same number of electrons as neon. When we write the charge, we always put the number first and then the sign. Now, I should have pointed that out over here. For beryllium, we don't put +2. We put 2+. For oxide, we don't put -2. We put 2-. We put the number first and then the sign. Sulfur wants 2 more electrons. If it gets 2 more electrons, it becomes sulfide. Selenium becomes selenide. Tellurium becomes telluride. Okay, so those are all minus 2. By giving them 2 more electrons, they have the same number of electrons as the noble gases in group 18. In group 15, here's nitrogen. Underneath nitrogen is phosphorus and arsenic. And nitrogen becomes nitride in 3 minus. Phosphorus becomes phosphide. Arsenic becomes arsenide. So they become minus 3. Because if you give nitrogen 3 more electrons, it has the same number of electrons as the noble gas nearest it. And those are about all of the monoatomic anions. Because carbon over here, it tends to not form an ion. And the other elements on the stair-step line, what do we call an element next to the stair-step line? It's a metalloid or a semi-metal. It's not exactly a non-metal. It's not exactly a metal. And so we don't have to worry about those. Those are the charges of the monoatomic ions. Okay? Now there's 2 more. There's a group. Well, let me say it this way. The thing you have to really watch to make sure you have it memorized in your long-term memory for as long as you do chemistry, you need to know the polyatomic anions. And this is where a lot of people make flashcards. Practice them until you know them. And I'll start off that there are 4 polyatomic anions that end in IDE. Now, all the monoatomic anions end in IDE. Usually, if you see something that ends in IDE, it's a monoatomic, but there are 4 important polyatomics ending in IDE. One is hydroxide, OH minus, hydroxide. And you just have to memorize that hydroxide is OH minus 1. CN minus 1. This is a polyatomic anion. It's called cyanide. Cyanide. Okay. O2, 2 minus, is called peroxide. And N3 minus 1 is called azide. So those are kind of unusual in that these are polyatomic ions, polyatomic anions that end in IDE. Usually if an anion ends in IDE, it's monoatomic. So fluoride ends in IDE. And then there are the oxyanions. An oxyanion will consist of oxygen plus another element. You know, the 2 best examples are sulfate, SO4 2 minus is sulfate, and nitrate, NO3 minus 1 is nitrate. Now, the periodic table is not extremely helpful in determining the charge, at least not at this point in the course. So you just have to memorize that sulfate is SO4 2 minus and nitrate is NO3 minus 1. But if you know sulfate is SO4 2 minus, then you automatically know sulfite. What is the formula for sulfite? It's SO3 2 minus. So it's just got 1 fewer oxygen, but the charge is the same. Sulfate is SO4 2 minus. Sulfite is SO3 2 minus. So if nitrate is NO3 minus 1, what is nitrite? NO2 minus 1. They both have the same charge. The ite has the same charge as the 8. It just has 1 fewer oxygen. So all I think you should do is just memorize the 8s, and then you can figure out the ites. Okay? Now, you've got to be careful about this because if you focus on nitrogen, this is nitrate, this is nitrite, but N3 minus for the periodic table, what's the name of N3 minus? Nitride. So the IDE almost always is used for a monoatomic. And then this is azide. N3 minus 1 is azide, and you just have to memorize those. So there are some anions you have to memorize. Okay, well, with that in mind, let's look at the top of the next page and write the formula for these ions. Now, the best way to learn these is to write these over and over. So I posted online an email from a student on this is on Blackboard. It's in the course materials. And he prepared a practice sheet where he had these over and over, and you write them in the blank. And he said he printed out about 20 pages of it and did it over and over and over. And within a real short period of time, it was seared into his memory. So that's what you want. You want to be seared into your memory so you can get it right. So potassium ion. So we go to the periodic table. Now, first of all, you have to know that potassium is the element K. And what charge will the potassium ion have? Plus 1. So potassium is in group 1, and so it forms a plus 1. So this is K plus 1. That's potassium. Then magnesium. You have to know that the symbol for magnesium is Mg. So here's magnesium. It's in group 2. So what charge does magnesium? It forms a +2, so Mg 2+. And here's aluminum. It's in group 13. What charge is the aluminum cation? Al3+ is aluminum. Okay. Now, if you see something like cobalt-4, there's a Roman numeral. So here's the element cobalt. You have to learn some of the element symbols. They're listed in the book. The ones in the table in the book. There's a table that says make sure you memorize these element symbols. Cobalt is right here, Co, but the Roman numeral 4 tells me that the charge is what? +4. So Co, and we write 4+. You're exactly right. We write 4+. That's cobalt-4. Now manganese. Now don't confuse magnesium, which is Mg, and manganese, which is Mn. Here's manganese. And manganese 2 has what charge? 2+. So see, there's nothing to memorize there. Okay, now ammonium, and I didn't review this with you, but there are a few polyatomic cations that you just have to memorize. And ammonium is one. Let me show you 2 of the polyatomic cations. Now you have to memorize that NH3 is the neutral compound ammonia. Now I know that you're familiar with ammonia. You can buy ammonia at the grocery store to clean your floors. When you buy ammonia at the grocery store, ammonia is really a gas at room temperature. Pure ammonia is a gas. When you buy ammonia at the grocery store, you're buying a solution of ammonia gas dissolved in water. It's neutral. It's a neutral compound. Ammonium is a cation, and it's NH4 + 1. It's what happens when you took ammonia and stuck an H+ on it. Remember, hydrogen is in group 1. It forms the +1 cation. So if you stick an H+ on ammonia, it becomes ammonium. Ammonium. Okay? And then, of course, H2O is water. So I want everybody to know the formula for ammonia is NH3. The formula for water is H2O. If I stick an H+ on water, I get H3O+. And what's the name of H3O+? It's hydronium. Hydronium. And then there's one other polyatomic cation that you have to know. There may be one other, but I'm just thinking one other polyatomic cation that you have to know. This is the hardest cation to learn, and so I will definitely ask it on the test. It's the hardest cation. All the cations are easy to learn. I'll definitely ask this one. It's Hg2, 2+. And this is called mercury 1, with the Roman numeral 1. Now that looks like that violates the rule that I gave you a minute ago. The Roman numeral told you the charge. But the difference is that Hg2, 2+ is a polyatomic cation. It has 2 mercury. So imagine that each of my fists is a mercury. Hg2, 2+, they're joined together as a polyatomic. You can't break it apart or it's not a polyatomic. Now why is it called mercury 1 if the charge is +2? Well, because there are 2 mercuries, and it's as if each mercury had a +1 charge. So the overall charge is +2. So that is a polyatomic. Those are the only polyatomic cations you have to know. And the hardest one is mercury 1. So this says ammonium. So what I do with ammonium, I think, well, ammonia is NH3. Therefore, ammonium is NH4 + 1. Ammonium is NH4 + 1. Okay, is everybody good with that? Next, you have to memorize bromide. When I see the IDE, IDE is almost always a monoatomic anion. And so I'll look on the periodic table. Bromine is a group 17 halogen. This is 16, 17. And bromide, then what is the charge of bromide? -1. One more electron makes it have the same number of electrons as krypton here. So bromide is Br -1. We just write Br superscript negative. That's bromide. IDE is used for monoatomic. Sulfide. IDE is almost always a monoatomic. So here's sulfur becomes sulfide. And so what is the charge of this sulfide anion? -2. It needs 2 more electrons to have the same number of electrons as the noble gas nearest it. So this is sulfide, S2-. We write S2-. Then nitride. Here's nitrogen. The IDE tells you it's a monoatomic anion. So for nitride, what is... I'm sorry, I didn't know if I was on the screen. Here's nitride. So what is the charge of the nitride anion? 3-, because it needs 3 more electrons. A neutral nitrogen atom has 7 electrons. It needs 3 more electrons to be like neon. So when I say a nitrogen atom, I'm saying it's neutral. When I say nitride, it's charged. It has 3 more electrons. It's 3 minus. Okay. So lead 2. What is the formula for lead 2? Well, first of all, you have to know that lead is Pb. The Roman numeral 2 tells me it's a cation. And what is the charge of the cation? 2 plus. So there's nothing to memorize. The Roman numeral tells you the charge. Now for the zinc ion, see this says write the formula for the following ions. So this just says zinc, but it's an ion. So there's no Roman numeral. So how do I figure this out? Well, I know that aluminum always forms what charge? Plus 3. And I'm going in this diagonal. So zinc is always what? Plus 2. So zinc is Zn2 plus. And silver right here in this diagonal, silver is always what? Plus 1. So it's Ag plus 1. You have to know that silver is plus 1. Now, remember, group 1 is always plus 1, group 2 is always plus 2, aluminum is always plus 3, zinc is always plus 2, and silver is always plus 1. But all of these other elements right here can be more than 1, and so we don't have to memorize anything. The Roman numeral gives you a way. Okay. Next, this says write the formula for chlorate and chloride. So all you have to do is memorize chlorate. Chlorate is ClO3 minus 1. You have to memorize that. And I would say go to the textbook. I've listed these in tables in a way that I think it's easier to memorize. Be sure you memorize that from chapter 2 of your textbook. So what is the formula of chlorite? ClO2 minus 1. So it has the same charge. They're both minus 1. If you memorize that chlorate is minus 1, then you know chlorite must also be minus 1. It's just got 1 fewer oxygen. The one that has 1 fewer oxygen than the 8 is the ite. So that's chlorite. Now that's different from chloride. I should have had here chloride. So what is the formula for chloride? What does the IDE tell you? It tells you it's monoatomic. And so chloride, if it's monoatomic, what is its charge going to be? -1. It needs 1 more electron to be like the noble gas next to it. So Cl minus 1. This is chlorate, this is chlorite, this is chloride, IDE. IDE tells you it's a monoatomic. So let's do nitrate, nitrite, and nitride. Now nitrate, you just have to memorize. Nitrate is NO3 minus 1. So what is nitrite? If you've memorized nitrate's NO3 minus 1, what is nitrite? NO2 minus 1. It has the same charge. They're both minus 1, but this has 1 fewer oxygen. Now, nitride, what does IDE tell you? It tells you it's a monoatomic, so I go to the periodic table. Here's nitrogen. What charge would you expect nitrogen to form in an anion? -3. It needs 3 more electrons to be like neon. So nitride is N3 minus. N3 minus. So nitride is different from nitrite. You have to watch that terminology real well. Okay. Now, some people see these two and they say, well, if it's the 8, it has 3 oxygens and a -1 charge. That's not true. You just have to memorize this because sulfate, it ends in 8, but it's SO4 and it's 2 minus. So you have to memorize that sulfate is SO4, 2 minus. So what is sulfite? SO3, 2 minus. SO3, 2 minus is sulfite. Now, I should go ahead and say, what is then sulfide? Sulfide. So the IDE tells you it's a monoatomic, and here's sulfur, so what will the charge of sulfide be? -2. So sulfide is S2 minus. So sulfate, sulfite, sulfide. Now this is our vocabulary, this is our alphabet, I should say. For as long as you do chemistry, you have to know all of these, or you will not pass the class. You have to memorize these and immediately know. For sulfate, it's not enough to know that it's SO4. You have to memorize that it's SO4 2 minus. It's not enough to know that it's 2 minus. You have to know it's SO4 2 minus for sulfate. You have to memorize that. It's not easy to get that off the periodic table. So one way or another, you have to memorize that. In lab next week, I think that you will have a lab workshop where you practice this. And there's a mnemonic that I put in there, something about Nick the Camel. Okay, Nick the Camel goes to Phoenix or something like that. And Nick the Camel goes to Phoenix. It's one way to memorize these. So if you're having trouble memorizing it, you can use the Nick the Camel goes to Phoenix. Or what, I forget what it is, but you'll do that in the lab workshop next week. Okay, any question or comment on this? Okay. Now let's write the following for the following compounds. Now, these are ionic compounds. In fact, I should tell you there'll be a clicker question tomorrow if you're in my, not tomorrow, we don't have class tomorrow, on Wednesday if you're in my class. There'll be a clicker question about one of these, or it's not on here, but is it ionic or not? And I'll give you the, here it is, it's ammonium chloride, which is an ionic compound because it exists the ammonium cation, NH4 plus, and the chloride anion, Cl minus. So you have to know that. So it's got these two ions. The formula for ammonium chloride is the neutral that we get when we have enough positives to balance the number of negatives. Now this is plus 1, this is minus 1. So the formula of ammonium chloride is NH4Cl. That's the answer. And this is an ionic compound. It has a cation and an anion. It is an ionic compound. That will be a clicker question in class on Friday. Okay. So let's look at each of these. So first I'm going to show you the work product, and then I'm going to give you the answer. The work process, first you name the cation. So sodium is the cation. I look on the periodic table. Here's Na. I have to know the charge of sodium. Sodium is Na plus 1. Everything in group 1 forms a plus 1 cation. So this is Na plus 1. Now nitrate, that's a polyatomic ion. I just have to memorize it. What's the formula of the nitrate anion? NO3 minus 1. Now that's not the formula for sodium nitrate. This is just the thought process I'm going through. To get the formula, it's got to be overall electrically neutral, which means the number of positive charges must equal the number of negative charges. Now in this case, I have a plus 1 and a minus 1. So I need one sodium cation and one nitrate anion. And so the actual formula here is NaNO3. And when we write it, we don't put any charges in it. This is sodium nitrate. Now, a shortcut that students like to use is called crisscross, where you take the superscript here and the superscript here and crisscross them. This is plus 1, so I'm going to have one nitrate. This is minus 1, I'll have, I'm sorry, this is plus 1, I'll have one nitrate. This is minus 1, I'll have one sodium. So the subscript for sodium is understood to be 1, and there's understood to be one nitrate, and so that's crisscross. And that works a lot of the time. Let's look at aluminum hydroxide. So I need the formula for the aluminum cation. What is the charge of the aluminum cation right over here? It's plus 3. So I'm going to write Al3 plus. Now hydroxide is a polyatomic ion. Usually if it ends in IDE, it's monoatomic. But hydroxide was one of those polyatomics. What's the formula for the hydroxide anion? OH minus 1. Now how many hydroxides do I need to make it overall electrically neutral with a plus 3? I need 3. This is plus 3, so I need 3 negatives. And so a way to do this is to crisscross. I'm going to bring 3 down here to the subscript down here, and this is a 1 that's understood to come down here. You never write a 1 subscript, but this will be then Al, and then I need 3 hydroxides. And to emphasize that I have 3, and this is polyatomic, I put OH in parentheses, subscript 3. So the 3 comes down here. The 1 comes down here, but I don't write the 1. So that's aluminum hydroxide. Okay, so when do we use parentheses? This is an important point. When do we use parentheses? We use parentheses if you have more than one of a polyatomic. Hydroxide is a polyatomic, and I need 3 of them. I only use parentheses if I need more than one of a polyatomic. Now up here I have nitrate. It's a polyatomic, but I only need 1 nitrate, so I don't use parentheses. Here, this is a polyatomic, but I need 3 of them, so I use the parentheses. I put the 3 on the outside. That says I have 3 hydroxides. Okay, magnesium. What's the formula for the magnesium cation? Mg2 plus. It's in group 2. It will form a plus 2 cation. So Mg2 plus. Now, acetate is one you just have to memorize. The 8. So there's several 8s that I ask you to just memorize. In fact, if you memorize, I think there's 7 8s. In all, you're going to know like 25 polyatomic ions. Okay, acetate is C2H3O2 minus 1. It's a longer one to memorize. That's acetate. C2H3O2 minus 1. Now, when I crisscross, I can bring this 2 down here and this 1 down here. The reason I'm crisscrossing is for every positive I need a negative. So this is plus 2, this is minus 1. I need 2 of these. So I'm going to bring the 2 down here. I need 2 of these. This is a polyatomic. If I need more than one of a polyatomic, what do I have to use? Parentheses. So this is Mg parentheses C2H3O2 close parentheses 2. Now, this is minus 1, and the 1 is understood to be down here. I'd never write a subscript 1. But this is the formula for magnesium acetate. This is the formula for magnesium acetate. Okay, is everybody good there? Okay. The next one, potassium bicarbonate. Now, one of the things that you need to know on the 8s is that if, I'm looking for a place where I can jot this down, it's what this prefix bi means. So over here, I'm going to write this over here, that if CO3 2 minus is carbonate, CO3 2 minus is carbonate. And you just have to memorize that. You can't get the charge or the number of oxygens easily off the periodic table. You just have to memorize that carbonate is CO3 2 minus. It's a polyatomic anion, which means there's more than one atoms making up this anion. Well, you can make another polyatomic anion by sticking an H plus on it. Do you remember how we stuck an H plus on ammonia to get ammonium? We stuck an H plus on water to get hydronium. Well, we can stick an H plus on this to get a new polyatomic anion. And if I stick an H plus on this, it's HCO3 minus 1. Now, I stuck an H plus, so instead of being negative 2, now it's just negative 1. And if you stick an H plus on an anion to get a new polyatomic anion, you name it with the prefix bi. So bi does not mean 2 in this context, bicarbonate. Bi means you stuck an H plus on this ion to make a new polyatomic anion. Now, I know this seems like a lot, perhaps. This is the first time you've approached this. You just have to practice this over and over until it becomes second nature. So this is bicarbonate. So over here, first of all, potassium. Potassium is K. What's the charge of potassium cation? Plus 1. So this is going to be K plus 1. That's potassium. Now, carbonate is CO3 2 minus. Bicarbonate is HCO3 minus 1. And to get the overall formula of the neutral compound, for every positive, I need a negative. So how many bicarbonates do I need for each potassium? Just 1. And so the formula is just KHCO3. That's potassium bicarbonate. Now, I don't use parentheses, even though this is a polyatomic, because I only have one polyatomic. If you only have one polyatomic, you don't use parentheses. Is everybody good? Okay. Iron 3 cyanide. So iron 3 is the cation. Now here's iron. Remember, we have to know that group 1 forms plus 1, group 2 forms plus 2, aluminum forms plus 3, zinc is plus 2, and silver is plus 1. But everything else is a variable charge cation. It can form more than one charge. So how am I supposed to figure out the charge of iron 3? It's the Roman numeral. The Roman numeral tells you that it's Fe 3 plus. That's what the Roman numeral means. So there's nothing to memorize. If you get a Roman numeral, you know the charge. Cyanide, this is one of the polyatomics that ends in IDE. Remember, there were 4 polyatomics that end in IDE. Usually, if it ends in IDE, it's one of these monoatomics right here. But there are 4 polyatomics: hydroxide, cyanide, peroxide, and azide. So cyanide, you just have to memorize, is Cn minus 1. That's cyanide. Now, if I do the crisscross, the 3 comes down here, the 1 comes down here, then I need 3 cyanides for each iron. And so this is going to be Fe, parentheses, Cn, close parentheses, subscript 3. So that's iron 3 cyanide. Now again, a lot of people, when they see iron 3, they think that means that there are 3 irons. But are there 3 irons in this? There's only 1 iron. The Roman numeral 3 means that the charge is plus 3. I have to use parentheses because I have more than one of a polyatomic. Does everybody see how I got that formula? Okay. Silver sulfate. What's the charge? What's the formula of the silver cation? Ag plus 1. See, there's no Roman numeral because this is +1, this is +2, this is +3. They're in a diagonal. You just have to memorize that zinc always forms the +2 cation, silver always forms the +1 cation. So silver is Ag + 1. What's the formula for the sulfate anion? That's one you just have to memorize. SO4 2-. Okay, so when I do the crisscross, how many silvers do I need and how many sulfates for this to be electrically neutral? 2 silvers and 1 sulfate. And so the formula for this compound will be Ag2SO4. I don't use parentheses. I only use parentheses if I have more than one of a polyatomic. Now I have more than 1 silver, but that's a monoatomic cation. So 2 silvers, 1 sulfate, and this overall neutral. When I write the formula, I don't write any charges in here, so Ag2SO4. Okay. Next we have calcium phosphate. So what is the charge of the calcium cation? Ca2+, it's in group 2. So Ca2+. Now, you need to memorize all of the 8s. So phosphate is PO4 3-. PO4 3-. So it's the first one that has a -3. Phosphate is PO4 3-. Now, when we do the crisscross here, the reason we have to do this, for every positive charge, there has to be a negative charge. And this is like finding the least common multiple of 2 and 3. The least common multiple of 2 and 3 is 6. If I have 3 calciums, the overall charge is +6. And if I have 2 phosphates, the overall charge is -6. So I'm going to bring the 2 down here, the 3 down here, and the formula will be Ca3 parentheses PO4 close parentheses 2. So I need the parentheses because I need more than one of a polyatomic. I bring this 2 down here, 2 phosphates, and bring the 3 down here, 3 calciums. So this is overall +6. 3 times a +2 is +6. This is overall -6. 2 times a -3 is -6. So all of the charge is balanced. That's calcium phosphate. Okay. Or how are you doing with that? Okay. Next we have ammonium. Ammonium is the cation. And you have to memorize, ammonium comes from ammonia. Ammonia is NH3. I want you to know that ammonia is NH3. So ammonium is NH4 + 1. So ammonium is NH4 + 1. Then we have sulfite. We have sulfite. And with sulfite, I never memorized sulfite, but I memorized sulfate. Sulfate is SO4 2-. So if sulfate is SO4 2-, what is sulfite? SO3 2-. Now again, you can do the crisscross. So how many ammoniums do I need and how many sulfites do I need for this to be electrically neutral? 2 ammoniums and 1 sulfite. So this is going to be in parentheses NH4 close parentheses 2 SO3. When do I use parentheses? I use parentheses if I have more than one of a polyatomic. Ammonium is a polyatomic cation, and I need 2 of them when I do the crisscross. I only need 1 sulfite. See, this is +1, and this is understood to be 1. So you don't use parentheses if you only have 1 polyatomic, but you use parentheses if you have more than one of a polyatomic. So this is ammonium sulfite. How are you with that? Okay. Now, we normally do not use number prefixes like di, tri, tetra when we name ionic compounds. But in science, there are exceptions to every rule. And this is an exception to the rule that we don't use di, tri, or tetra with ionic compounds. And it's in the case of dihydrogen phosphate. And that's because if I write over here on this side, you have to memorize that phosphate is PO4 3-. That's phosphate. But there are 2 other polyatomic ions. If you stick an H+ on phosphate, if you stick 1 H+, you get HPO4 2-. So instead of being 3-, it's 2- because I put a +1 on here. H is +1. Now, up here, if I stick an H+ on carbonate, it becomes bicarbonate. But I have never seen this called biphosphate. This is called just hydrogen phosphate. It's a polyatomic ion, hydrogen phosphate. Hydrogen phosphate. Didn't have enough room there. But if I stick 2 H+ on phosphate, I get H2PO4 -1. That is a polyatomic anion. Polyatomic means that all the atoms work together to make one anion. It always acts as a unit. And how do you name this? Well, you name this dihydrogen phosphate. This is dihydrogen phosphate. This is the one time you'll see the di prefix used in an ionic compound, dihydrogen phosphate, because it's a polyatomic ion. So as I look at this, what is the formula of the magnesium cation? Mg2+. Magnesium is Mg2+. What is the formula of dihydrogen phosphate? Dihydrogen phosphate is the anion. It's a polyatomic anion. It's H2PO4 minus 1. Now, when we do the crisscross, for every one magnesium, I need how many dihydrogen phosphates? 2. So the correct formula is Mg parentheses H2PO4 close parentheses 2. That's magnesium dihydrogen phosphate, because this is a polyatomic anion. Now I'll go over these polyatomic ions in class in a little more detail, but this is how we go about doing it. That's one of the hardest ones we've done so far. Do you see how we get that done? Okay. Potassium permanganate. What's the formula for the potassium cation? K plus. You know, I've repeated potassium and magnesium and calcium because those are very common. You'll see them all the time. So K plus is potassium. Now permanganate, that's one you just have to memorize. Permanganate is MnO4 minus 1. MnO4 minus 1. This is plus 1, this is minus 1. It's just a 1-to-1 ratio. So potassium permanganate is KMnO4. KMnO4. Okay, so this gives you a preview of what we're going to do in class on Friday. How are you doing with this so far? Okay, next. How do you name acids? Well, the rule is the name of an acid is based on the name of the anion. Okay? And an anion will either end, if the anion ends in "ide" or "ate" or "ite", then the acid, the name of the acid, is different depending upon whether the anion ended in "ide", "ate", or "ite". So, if the anion ended in "ide", then the acid will have a hydro prefix and an ic acid suffix. Now I think that's easier than it looks for most of you, because most of you know the formula for hydrochloric acid. So let's see, do I have that as one of my examples? It's not, so I'm going to write right here. HCl comes from chloride, which ends in IDE. And most students, when they first come to class, they already know that HCl is hydrochloric acid. If you know that, then this is the model that we will follow, that if the anion ends in "ide", the acid is like hydrochloric acid. It has a hydro prefix and an ic acid suffix. You change the "ide" to ic acid. Okay. If the anion ends in "ate", you don't use the hydro prefix. The only time you use the hydro prefix is if the anion ends in "ide". If the anion ends in "ate", then the acid is just going to end in ic acid. And if the anion ends in "ite", then you'll change the ending to us acid. Us acid. Okay, so I have a corny way to remember this. "Ate" becomes ic, "ite" becomes us. I call this the McDonald's rule. I actually like McDonald's, but I call this the McDonald's rule. It's "I ate and got sick." I ate and got sick. If the anion ends in "ate", you change the ending to ic. I ate and got sick. And then you can say a humongous bite. Humongous, look it up in the dictionary, it ends in us. A humongous bite. So "ite" becomes us, just like humongous bite. Okay, so let's look at this. This is hydroiodic acid. It's got a hydro prefix and an ic acid suffix ending, so it comes from iodide. Now, the IDE in iodide tells you it's monoatomic. So what is the formula for the iodide anion? Iodide is I minus. So hydroiodic acid, to make the formula for the acid, you stick enough H pluses on it to make it neutral. Hydroiodic acid is HI. HI. And I'm going to put aqueous here. Aqueous means dissolved in water. It's called hydroiodic acid. It comes from iodine. Okay. Now here's hydrosulfuric acid. It's got a hydro prefix and an ic acid. So it comes from sulfide, IDE. The IDE ending is sulfide, hydrosulfuric acid, IDE. And sulfide, the IDE is almost always monoatomic. So what's the formula for sulfide? S2 minus. So what's the formula for hydrosulfuric acid? It's H2S aqueous. H2S aqueous, dissolved in water. It's called hydrosulfuric acid. Hydrosulfuric acid. So the hydro prefix and the ic acid tells you it came from ide. And you stick enough H pluses on it to make it neutral. So this is hydrosulfuric acid. Now sulfuric acid, and actually this is the two acids that I would bet 90% of the students in Chem 1441 already know are hydrochloric acid, HCl, and sulfuric acid, H2SO4. So I hope you already have this memorized. Now if you don't, be sure you learn it. Those are two of the most important acids, sulfuric acid, H2SO4. But sulfuric acid, it doesn't have the hydro prefix, so when I see ic acid, I think McDonald's. I ate and got sick. Actually, I don't get sick when I eat McDonald's. I love McDonald's. Just saying McDonald's, my mouth is watering. I'm hungry right now. I could go for a Big Mac and large order of fries right now. But ic acid, I think the McDonald's rule, I ate and got sick. And so this comes from sulfate. And I have to know the formula for sulfate. Sulfate is SO4, 2 minus. And so you stick 2 H pluses on it. Sulfate is SO4, 2 minus. And so sulfuric acid is H2SO4. Now, in this case, we add a syllable to make it sound better. So sulfate, we don't just call it sulfic acid. We don't just change, in this context, the ate to ite. We add the syllable sulfuric acid to make it sound better. But still, that ends in ic acid. So up here, this is hydrosulfuric acid. It's different from sulfuric acid. Hydrosulfuric acid comes from the sulfide anion. Sulfuric acid comes from the sulfate anion. Okay. The next one is phosphorus acid. Now before doing phosphorus acid, let's come over here and do phosphoric acid. Now the ic acid here for phosphorus acid is the McDonald's rule. I ate and got sick. So first, you tell me what's the formula for phosphate, the phosphate anion. PO4, 3 minus. So phosphate, it's like sulfuric acid. It sticks another syllable in to make it sound better. So it's not going to be phosphic acid, it's phosphoric, but it still ends in ic acid. Phosphate becomes phosphoric acid. I stick enough H pluses on to make it neutral. So what is the formula for phosphoric acid? H3PO4. Now this is phosphorus acid. So phosphorus acid, what's the name of the anion that this comes from? So it's I ate and got sick, a humongous bite. So what's the name of the anion? It's called phosphite. And what is the formula for phosphite? See, ite and us acid. So what's the formula for phosphite? Well, I didn't memorize phosphite. I memorized phosphate. All I did was memorize the eights. If you memorize like 7 eighths, you can know all of these. You know all 25 anions. Phosphate's PO4, 3 minus. So what is phosphite? PO3, 3 minus. So what's the formula for phosphorus acid? H3PO3. Phosphorus acid, the OUS tells you it comes from the ite. Okay. Nitrous acid, what's the name of the anion that nitrous acid comes from? What? Nitrite. Exactly, nitrite. Now, I didn't memorize nitrite. I memorized nitrate. Nitrate's NO3 minus 1. So what is nitrite? NO2 minus 1. So what's the formula for nitrous acid? HNO2. I stick enough H pluses on to make it neutral. This is minus 1, so I need 1 H plus. Nitrous acid, HNO2. Are you with me? Okay. I'm sorry, I was off script. Nitrous acid is HNO2. Hypochlorous acid. Hypochlorous. So that's not hydro, that's hypochlorous. And here's where, in the polyatomic anions that you have to memorize, and I'm looking for a place to write this. I kind of used up all of my space here. I'm going to go back to the bottom of page 116, and I'm going to show you 4 ions: ClO4 minus 1, ClO3 minus 1, ClO2 minus 1, ClO minus 1. Now, I've only memorized one of those, and the one that I've memorized is ClO3 minus 1 is chlorate. All I do is memorize the A's. That's chlorate. So what's the name of ClO2 minus 1? Chlorite. And if it has one fewer oxygen than the ite, then we put a prefix on it, which is hypo. This is called hypochlorite. Hypochlorite. Now the prefix hypo means under. So this, it's got one oxygen under than the chloride. It's like hypodermic. What's a hypodermic needle? It goes under the skin. Hypo means under. Now, one more oxygen. See, hypo means fewer oxygens, and one more oxygen in the 8. Actually, they originally proposed it be called hyper. So more is hyper, and fewer is hypo. But hyperchlorate didn't sound good, so they took the high off and just called this perchlorate. But it came from hyperchlorate, perchlorate. So if it's got one more oxygen in the 8, you put a per prefix on. If it's got one fewer oxygen in the ite, you put a hypo prefix on. So I didn't remember, the only one I memorized is chlorate. But I can always figure out what hypochlorite is. So I go over here. Hypochlorous acid comes from hypochlorite. Now, chlorate is ClO3 minus 1. Chlorite is ClO2 minus 1. So hypochlorite is ClO minus 1. So hypochlorous acid is HClO. Now, it can also be written as HOCl. You'll see it written both ways. I want you to recognize both of those. Those are two alternate ways. The reason it's often written this way is this is how the atoms are attached. The hydrogen is actually attached to the oxygen, attached to the chlorine. Now look at the number 7. How would you guess that you would pronounce number 7? You would assume periodic, but it's not periodic. It's periotic. It's periotic acid. And it comes from periodate. Periodate. Now, once again, if you know chlorate, you can know this because chlorine, bromine, and iodine are all in the same group in the periodic table. So if chlorate, let me move this. If chlorate is ClO3 minus 1, iodate is IO3 minus 1, the same number of oxygens and minus charge. And periodate is IO4 minus 1. Now, I'll go in more detail on this in class, but let me just list it. Periodate is IO4 minus 1. So periodic acid is HiO4. It's HiO4. So you see the ic acid, and you know it came from periodate. So all you have to do is figure out what is the formula for the periodate, and then stick enough H pluses on it. And I'll show you how you can know, in class, pay attention to this, because I'll show you that if you know chlorate, you automatically know periodate. If you know chlorate, you know in all 12 polyatomic ions. If you memorize that chlorate is ClO3 minus 1, then you will know 12 polyatomic ions. So pay attention to that in class. Now, carbonic acid comes from carbonate. What is the formula for carbonate? It's CO3, 2 minus. So what is carbonic acid? See, this is the McDonald's rule. Ic acid, I ate and got sick, so this is from carbonate. Carbonate, CO3, 2 minus. So what's the formula for carbonic acid? H2CO3. So do you see how it all goes back to the anion? If you learn the anions, you can name the acids. So bromous acid, that comes from what anion? What's the name of the anion? Bromite. I ate and got sick, a humongous bite. Us goes with ite. So bromide, I need to know what bromide is. Well, remember, if you learn chlorate, you actually know 12 ions, because right underneath the chlorine is bromine. So chlorate, ClO3 minus 1 is chlorate, so BrO3 minus 1 is bromate, and BrO2 minus 1 is bromite. Now, I'm doing this kind of quickly because we're here at the end, we're about to run out of time, but we'll do this in class. Bromite is BrO2 minus 1. How do I know that? Because bromate is BrO3 minus 1. How do I know that bromate is BrO3 minus 1? Because chlorate is ClO3 minus 1. So bromous acid is HBrO2. HBrO2. Okay, and the last one, we'll stop with this, hydrocyanic acid. So this has a hydro prefix and an ic acid suffix, and that's like hydrochloric acid. Now, hydrochloric acid comes from what anion? What's the name of the anion that you get hydrochloric acid from? Chloride. So this comes from what anion? Cyanide. So you have to memorize cyanide. Now, usually the IDE is a monoatomic, but cyanide is one of the polyatomics you have to memorize. What's the formula for cyanide? Cn minus 1. So hydrocyanic acid is just HCN, aqueous. Okay, I hope this was helpful. I know we've gotten a little ahead of class, but when I go over this in class, maybe it will make more sense to you as well. Be sure you know how to name things. That's the main learning objective of Chapter 2, is being able to name things. Hope this was helpful. Have a good evening.
Thank you.
You're very welcome. Yes.
So, anytime you add in hydrogen, you take away.
Yes, you're adding an H plus, so it lowers the charge. This was a -3. When I put 1 H plus in, now it's -2. If I put 2 H pluses in, it's -1. And if I put 3 H pluses in, like phosphoric acid, it's neutral. So every H has a +1 charge. And so it changes the overall charge. See you next time. Thank you, too. See you later.
Also, do you always have organization for today?
Yeah, every Wednesday from 3:30 to 5 in this room for Chemical 241.
Oh, thank you.
You're welcome.
Now when Johnny